The images you are seeing right now have been a closely guarded secret for years. This is the first time footage of this technology has been shared publicly. A technology that has the potential to change the course of human history. A privilege Helion Energy granted us when we visited their facility. What I am sharing right now is going to be studied by nuclear physicists around the world, trying to reverse engineer the world-changing machine. This is Trenta, Helion's 6th generation nuclear fusion generator. This fusion generator is unlike any other, using a completely novel approach to achieve nuclear fusion, adapting knowledge developed for ion propulsion in space. The generator forms 2 mirrored rings of plasma on either end of a reactor, and in a 1/10 of a 1,000th of a second, they fire them at each other, sequentially activating powerful magnets to squeeze and compress the rings towards the center, where they collide, converting the astonishing kinetic energy of the ions, traveling at 300 kilometers per second, into thermal energy, raising the plasma temperature to tens of millions of degrees, hot enough to overcome the electromagnetic repulsion keeping the ions apart, and allowing them to fuse, forming new atoms and releasing a tremendous amount of energy in the process. This isn't the world of fairy tale. This is already happening. I watched the bright pink flash of fusion multiple times inside the control room of Trenta, safe away from the gigawatts of power surging through the capacitor banks of the reactor. It became mundane pretty quickly, to the point that my reaction to the feat became oddly subdued. But make no mistake, what Helion has achieved here is astonishing, initiating nuclear fusion reactions with ease. So let's jump into it with Helion's brilliant founder, David Kirtley, giving us the world's first tour of Trenta.
Welcome to Helion. Can you just start explaining what this machine is?
Yes, so you're at Helion's Redmond facility. Here we're standing in front of our 6th generation machine. We call this one Trenta. This is the 6th generation of machines that form, merge, and compress fusion plasmas to fusion conditions doing fusion.
We're looking at this end of the machine, but it's mirrored on that end. Can you explain why you do the pulse reaction towards each other?
Yeah, it's a great question. The fundamental concept of how these systems work is unlike most fusion. And here we inject a fusion target. We call this one a field reverse configuration. Then using pulsed magnetic fields to very high pressures, we compress that fusion plasma up to fusion conditions. One of the challenging parts is how do you get that target, that initial fusion fuel, into the compression chamber and do it in a repeatable, symmetric, high energy way. And so one of the things that we pioneered was a concept of merging field reverse configurations, merging these plasmas, where we actually have a symmetry on either side of the machine. We have these injectors, we call them the formation section, where we actually form this initial plasma. We inject the fusion fuel. We then accelerate them, merge them in the center region, where they take all that kinetic energy that we put into them when we accelerated them, and they stop. They stagnate, converting that kinetic energy into temperature, into thermal energy, and that starts the fusion reaction. We then can compress it all the way up to the full fusion conditions.
Okay. And the actual plasma generation happens on this end, right?
The plasma generation happens right here, interestingly enough. So over here, we're standing in front of what is called the diverter. This is what happens after the reaction. Here is our formation section. Here is where we initially inject our neutral gas. So the gas is ejected from a flow manifold, a fuel manifold here, where we puff in gas in a neutral gas that's just at room temperature. This gas fills this chamber over the course of several thousandths of a second. At this point, it's room temperature, it's very low pressure, a fusion fuel mix of deuterium and helium-3. We then ionize that gas. What that means is we start to heat that with a combination of RF and electric fields, which then take the electrons that are orbiting the nucleus and tears them off of the nucleus, forming a plasma, charged particles, positive and negative charges in this area. We then form what is called a field reverse configuration, where what we do is we take magnetic field that's keeping this plasma. This part, it's ionized. It's, for us, relatively cool. It's about 1,000,000 degrees. But that's still so hot that it can't touch any of the walls without damaging materials. So to prevent that, we have magnetic fields that thread through this entire machine, keeping that hot fuel, that hot fusion fuel plasma off of the walls. But what we do here, which is quite unique, is that we then take that initial magnetic field and by pulsing at very high intensity, over 100,000 amps per coil, we then reverse that magnetic field, trapping magnetic energy in a closed field. This is called a self-confined, self-organized plasma. It's a really unique version of fusion fuel that Helion and very few others do. But what that enables us to do is form a closed magnetic topology, a closed plasma object that we can do things to, we can actually do work on. And so at that point, we now have a closed field reverse configuration in this formation section. We then start to pulse these magnetic field coils at high pressure, sequencing them. And they get sequenced as we go down. We call that peristaltic acceleration, like squeezing a tube of toothpaste. It accelerates that plasma out of the formation section, which had all the complex ionization, gas injection, and all those things, into higher field section. At this point, we've now moved into what we call the acceleration section, or the plasma injector, where literally here, we are now continuing to accelerate this plasma to over 1 million miles an hour, 300 kilometers a second and higher, down the length of the system. But as we do that, we start to compress it already. So as we increase the magnetic field through adiabatic compression, ideal gas law, as you increase the magnetic pressure, the plasma then compresses, decreasing in radius, but increasing in pressure and temperature. So as it's left the formation, it's on the order of several million degrees. But now we start to compress it, we start to accelerate it. And if we've done everything right and sequenced these in just the right way, this plasma field reverse configuration has now accelerated all the way to 300 kilometers a second. It's heated to on the order of 10 million degrees. And then we inject it into the main compression section. You notice here, the bolts, the pressure, everything goes up, because here's where we really do the fusion. If we've done everything right, this FRC, that we've injected into the main compression section, has met its mate that we made symmetrically on the other side. And what they do is those two collide. Those two plasmas collide, and here's the really important part, they stop. They stagnate, they take all that kinetic energy we added, all that velocity, and we turn that into thermal energy. It superheats up. And if you've done everything right, in the middle of this, you have a system that's on the order of 10 to 20 million degrees, sitting in this main compression section, ready to do fusion. So now you rapidly, as fast as modern technology will allow, we increase the magnetic field to high pressure, compressing that fusion plasma all the way up to fusion conditions, over 100 million degrees. Fusion begins, large amount of fusion is happening. Inside this core compressed FRC now, this core compressed fusion fuel, the fusion reactions start to occur. Those fusion reactions are creating new particles. Deuterium fusing together with helium-3 to form helium-4 and an extra hydrogen. And both of those two particles are very high temperature now. They're born inside the fusion plasma, applying pressure back on these magnetic fields. That works just like in a piston, where in a piston you compress the fuel, it begins to burn, it then gets hotter, it pushes back on that piston, only we do it all electromagnetically.
This is a truly innovative concept. With tokamak reactors, like the massive ITER reactor being built in France right now, electricity is created by converting the kinetic energy of neutrons expelled during fusion to heat, by slowing them down in the blanket walls. This heat is then transferred to high-pressure water to create high-pressure steam, which turns a turbine attached to an electric generator that rapidly rotates a magnetic field around copper wires to generate an electric current. Helion is skipping steps 1 through 4 and going straight to moving a magnetic field around copper wires, generating electricity directly from the magnetic field, cradling the fusion reaction at the center of the machine. As the fusion reaction occurs, the energy it generates begins to push back on the magnetic field confining it, moving it, as David said, like a piston. It's this changing magnetic field that will generate Helion's electricity. Skipping all the initial steps needed to boil water and turn a turbine should, in theory, make it vastly more efficient, while also unlocking the major benefits of a superior nuclear fusion fuel mixture. One of the problems with tokamak reactors is their choice of fuels. The fuel mixture of choice for tokamaks is deuterium and tritium. The availability of deuterium is not a problem. It's everywhere. This is a bottle of heavy water. Water with 2 deuterium atoms instead of 2 regular hydrogen atoms. It's cheap and safe. I can even drink it. However, tritium, as we spoke about in more detail in our last video, is extremely rare. We only have about 20 kilograms of it in global reserves, and a single commercial-scale tokamak is expected to burn through 300 grams of it a day, giving us about 2 months of operation with the world's entire current supply. Tokamak generators will manufacture tritium on site using a lithium breeding layer. When the high-energy neutrons from our nuclear fusion reaction collide with the lithium in the reactor wall, the lithium splits into tritium and helium. This is a reasonable solution, but 80% of the energy of the tritium-deuterium fusion reaction is carried by those high-energy neutrons. So, we have effectively wasted all of our energy to get back to square one. To combat this, the first layer of tokamak walls will be made of beryllium, a neutron multiplier, which creates 2 neutrons when struck by 1 neutron, giving us 1 neutron to create tritium and 1 neutron to generate heat. However, beryllium is extremely expensive. The entire annual global supply is just enough to build a single tokamak generator. Beryllium also contains uranium impurities, which will be encountering the high-energy neutrons too, making the beryllium blanket dangerously radioactive over time, which will make disposing of it expensive. This all points to one massive problem. Tokamak reactors are going to face the exact same issues as nuclear fission energy. They will be too expensive and won't be able to compete with cheaper forms of electricity. This is why Helion is using a completely different fuel mixture.
So Helion's approach to fusion uses a deuterium and a helium-3 fuel. Deuterium is really common. It's 1 part in 500 in all water. It's in the coffee you drink. And safe and readily abundant and low cost as well. We buy it in compressed gas cylinders. It's already purified, but you could imagine doing the purification yourself. It's pretty straightforward. The helium-3, however, is ultra rare. And in fact, while helium-3 was theorized in the early days of fusion as being the best fusion fuel, because of its rarity, there haven't been a lot of approaches that have used helium-3 or demonstrated helium-3. To our knowledge, Trenta was the first system we know about that did bulk deuterium helium-3 fusion for a power generation application. One thing Helion has done is we patented a helium-3 process of creating helium-3, of taking 2 deuteriums found commonly in nature and at high pressure in a fusion system, ironically, fusing them together to form helium-3, taking 1 more deuterium, fusing that with the helium-3 to make helium-4, and that's what makes the electricity.
So it's only the reaction of the deuterium with helium-3 that generates the...
The deuterium with the deuterium generates some amount of electricity, a small amount. It generates about 1/8 of the deuterium helium-3 reaction.
What influences that?
So what influences the amount of power output per reaction is the actual atomic physics that's happening, where when 2 deuteriums combine, they have a few reactions, but the one we care about most will create a helium-3. And that helium-3 will have a lower mass deficit, so the amount of missing mass of that final product. So E equals mc squared, and that mass deficit is the amount of energy that's released in terms of the particles that are created and their temperatures. And so deuterium helium-3 has a larger mass deficit when it forms helium-4, and so you end up with more energy trapped in that helium-4 as well as in the other proton that is made.
There's quite a lot to break down there. As David said, the energy released depends on the mass difference in the final reaction. But how we can capture that energy changes with the products that are created too. 2 types of fusion can occur when fusing 2 deuterium atoms. One creates a helium-3 atom and a neutron. Most of the energy of that fusion event is carried away by that neutron. Tokamak reactors generate electricity by converting the kinetic energy of neutrons to heat in their walls. But Helion's energy capture system can't generate electricity with neutrons, because they have no charge. Helion needs charged particles to push back against the magnetic confinement to generate electricity. That neutron just flies right through the magnetic jail. The helium-3, however, carries about 0.82 mega electron volts of useful energy that the generator can capture. In a second possible reaction, deuteriums can create a proton and a tritium, with the proton carrying 3.2 mega electron volts of energy and the tritium isotope carrying 1.01. Helion's generator will capture as much energy as possible from these particles before exhausting them through the turbomolecular pump in the diverter section, with the protons regaining an electron and becoming hydrogen, and the radioactive tritium being transferred to remote storage. Here, it will beta decay into helium-3, but this process takes 12.3 years to occur. When it finally does decay, that helium-3 can be fed back into our generator. So, Helion has two pathways to create helium-3 for their primary fusion energy reaction. When deuterium and helium-3 combine, they create a helium-4 atom and a proton, releasing 18.3 mega electron volts, more than the 17.6 mega electron volts released from deuterium and tritium reactions. And on a mass basis, 4 times more than a uranium fission reaction. Being able to generate your fuel right where you need it is a huge advantage, but David Kirtley had an interesting alternative.
It's a very good business case of you could do it that way, or you could do it where you have one dedicated facility and all it does is fuse deuterium and make fuel and then put it in a bottle, separate it from all the other gases, and then ship that to your generators and have the generators just make electricity and not deal with the fuel processing. I think that's a good, outstanding business decision that we don't know. One of the things that you have to keep in mind is when you do the deuterium fusion, that's when you make the neutrons. So the neutrons come from the deuterium fusing together. And so there's some really maybe advantageous things of separating those two machines.
One of those advantages is prolonging the life of our generator. The high energy neutrons from the deuterium-deuterium reaction can damage our generator. This is a huge problem for tokamak generators because 80% of the energy in the deuterium-tritium reaction is carried by the neutron. But the neutron generated when 2 deuterium atoms fuse has 5 times less energy, reducing the damage it can do. However, they are still damaging. If we could design a cheaper, more robust reactor purely to create our fuel products, that could be economically beneficial, especially if there are multiple generators that all need fuel supplies. Replacing one fuel generator that can feed 10 energy generators is a lot cheaper than replacing 10 hybrid fuel and energy generators. So, there are many benefits from moving away from deuterium and tritium, but the deuterium and helium-3 reaction does require higher temperatures, and this does pose an engineering challenge, especially as Helion progresses to their commercial scale reactor.
So right now we're building Polaris, their 7th generation system. The goal is that it will demonstrate electricity production for the first time, come online in 2024. The stepping stone between our 7th generation system, we're building Polaris, and the 8th generation system is a lot of the engineering around the system, that we want to turn up the power output, the yield even further. We want to make sure we're taking the electricity that we're recharging capacitors with, turning that into 60 hertz AC and putting that on the grid. And then also repetition rate. That's a big one, is that going from operating every few seconds to now operating multiple times a second is another engineering leap we have to make in some of the thermal engineering, structural engineering, and gas handling systems.
What do you think is going to be the biggest challenge in making that jump?
I think if you ask any engineer or scientist on my team, you're actually going to hear a different answer for what is the hardest thing that we're trying to solve. My personal belief in building the steady operating systems that we built in the past is it comes into the thermal operation of these systems. Whereas things start to heat up, they change. The structural mechanics change of these pulsed magnets. The way the fusion plasma actually the wall temperature changes as it changes in temperature. We saw that on our earlier subscale systems. And so we expect to see that on the big scale systems too. And so understanding that, predicting that, and then engineering all of the mechanisms in place for that, I think are going to be some of the most exciting engineering challenges that we're solving right now. And so we're hiring those teams to solve those problems right now.
Were there any surprising learning moments recently that you've discovered with Trenta?
There were some exciting things that we learned on Trenta that were unexpected. We were really worried early that the timing accuracies of merging these two high-speed plasmas over 1 million miles an hour, compressing them, working on getting their alignment, that would be really a tough challenge. And what we found that is, in practice, it's actually quite a bit easier than the theory or the basic computation simulations would actually show, that we can, with a lot of essentially freedom, merge these and get really good results that are really repeatable. Some of the things we did find, however, that are a little bit more challenging is as these plasmas got hotter and we got above 10 million degrees and got to the 100 million degrees, what we found is that there's probably some other effects, good effects, where we're producing more fusion than we maybe predicted, but the fusion plasma interacts with the vacuum chamber a little bit more than what we thought as well. And so what we're having to do for future systems is build them just a little bit bigger, about 25% bigger than what we'd originally planned to account for those things. And so there's some engineering iteration that has to happen as we discover the advanced physics and the engineering of implementing these systems in practice.
This is another one of the benefits of Helion's system. It's a much smaller generator than other generators like ITER's tokamak, which makes iteration far easier, as larger machines will be more expensive to build, making the capital cost of learning a much larger barrier. Polaris is their 7th generation system, and it's 25% bigger precisely because of the lessons learned from Trenta. The physics of fusion is a new frontier. There are few textbooks to learn from. Helion is helping write the first textbooks, and one of the things they discovered is that gyro orbits are larger than they expected. A gyro orbit is essentially the radius at which those fuel ions orbit around magnetic field lines. It's affected by the temperature and thus the speed of the ions and the magnetic field strength. Helion discovered with Trenta that these orbits are larger than simulations calculated, which meant the ions could impact the generator walls, and given their temperatures, this was a no-go. So, Polaris is 25% larger to account for this discovery. Polaris will also be the first generation to begin capturing electricity, but that's a lot easier said than done, and will need the very latest electronics to work quickly enough. Under Trenta, there are stacks upon stacks of capacitor banks. 90% of Trenta's power goes towards generating the huge currents needed to generate its magnetic fields. The magnets that form and push the plasma forward run at 100,000 amps, while the main compression coils at the center of the machine run at 1 million amps. Drawing that kind of current from the grid is impossible, so Trenta needs a way to store power locally and discharge it quickly to achieve the necessary current. Batteries can't discharge that quickly, so Helion is relying on capacitor banks. We took a look beneath Trenta to learn more about them.
So what you're seeing here, this is actually one capacitor unit. And so if you're used to other electronics, a capacitor...
Each of these boxes is one unit?
Each of those boxes is one capacitor that has several kilojoules worth of energy storage in it. And then we have hundreds of those capacitors that all in parallel in a modular way make the main bank. In parallel to that are other capacitors that are slower response, higher efficiency. Those are run with semiconductor switches. And then even some capacitors that are very old, that are maybe 20 plus years old, that we use for some of the formation sections and some of the initial ionization sections.
Any issue with them being older? Is that just like the length of time you've been working on this technology, you just had these lying about, or is it better to use newer?
It depends. So what we've seen is over the years, the way the pulse power technology and community has evolved, some of these capacitors are actually still the highest performing capacitors because the industry doesn't manufacture a lot of these for our type of application. Now, one thing you'll see later in our facility, Antari's facility in Everett, is our new capacitor manufacturing line where we're making custom capacitors designed for exactly this application. And those outperform even the older technology.
Is there any issue with just the rate that when you get up to faster pulses that these might deteriorate over time, or?
Yeah, so one of the keys to these systems is as you're running them, what we call repetition rate, where you're pulsing not once every 10 minutes like Trenta does, but where you're pulsing every 10 seconds, or once a second, or 10 times a second. Now, the lifetime of the capacitors, their ability to handle throughput, average throughput, and the heating in the capacitor starts to become engineering issues that we have to consider. Luckily, as we've evolved, so has the capacitor technology, and so self-healing and other capacitors that have long life, maybe not pulsed, but are long life, those capacitor technologies are now enabling for us to do this. On subscale systems, not on Trenta, but Trenta has done over 10,000 high-power pulses doing fusion. In some of our subscale systems that we did earlier that they weren't doing fusion, but were making these types of plasmas, we've done not tens of thousands, but we've done billions of discharges with capacitors and run them steady for months on end at hundreds of hertz. So we have a lot of experience in building steady operating pulse power systems that are quite a bit smaller than this. And so a lot of the work we have now is taking those experiences and that engineering experience that we have at Helion and combining that with the large scale pulse power fusion systems and merging those two together into the Polaris system.
With the size of this capacitor bank, you would think it holds an astounding amount of energy. But the total capacity of the bank is just 10 million joules, the equivalent energy of about 22 bananas. Or, in terms of a typical Tesla battery pack, that's 2.8 kilowatt hours, 1/30th the capacity of a typical Tesla battery. However, we aren't expending that energy in an hour. We are releasing it in 100 microseconds. These capacitors release a lightning bolt of current through the machine, gigawatts of instantaneous power. But it isn't an uncontrolled burst of electricity like a lightning bolt. It's a carefully controlled orchestra of switches, releasing and controlling this much electricity with a microsecond precision simply was not possible when the concept was first envisioned. Within those 100 microseconds, thousands of operations occur across the machine. Each row of electromagnets along the machine need to activate 300 nanoseconds after the previous. They need to trigger just as the plasma passes by, traveling at millions of kilometers per hour, to push it even faster towards the center. That would be impossible without modern-day microprocessors and fiber optics. And even then, Helion needs to factor in the speed of light through the glass fibers, the time it takes for a current to propagate through a tiny semiconductor switch, and account for every other delay in the system. Legacy electronics simply have too wide margins of error to account for those delays properly. Without fiber optics, those millions of amps traveling through the system would induce currents in other parts of the machine and create misfires. What Helion is doing right now is astounding. The sequence of events to cause fusion in this machine is a delicate symphony of electronics, pushing two plasma rings into a violent collision and catching that collision in a magnetic trap in the center, which proceeds to shrink until the ions trapped within it have nowhere else to go but to fuse, overcoming one of the universe's strongest forces to create new elements in the belly of a man-made machine. But Helion isn't done. They are already building the next step in their quest for clean, safe energy for humankind with their 7th generation machine, which will do everything Trenta can do, but faster, and add another process, capturing the energy of the expanding plasma to generate electricity, adding even more complexity to the delicate symphony, with the energy flowing back and forth from capacitor banks like the tides on a shore. And hopefully, if all goes according to plan, each turning of the tides will push a world-changing electricity source onto our grids. I have never been particularly hopeful that nuclear fusion power was ever feasible, but speaking with David and all of the talented staff at Helion, and the recent news from the US Department of Energy about their net energy output from their inertial confinement reactor, it has really made me feel that this technology may not just be possible, but potentially around the corner. We shot hours of footage at Helion, and cutting it down into a cohesive and entertaining YouTube video meant that a lot of interesting information was left out. It would be a shame for those interviews to be stored on our internal servers, never seeing the light of day. So I have made 2 of the longest interviews available to watch for our Nebula subscribers. which you can get access to with an even lower price due to our 42% holiday discount, giving you the Nebula and CuriosityStream bundle deal for just $11.59 for the entire year. Less than $1 a month for access for yourself, or you could buy it as a gift for the holidays. The full uncut tour of Trenta and our standing interview with David Kirtley are both available on Nebula right now. We are aiming to do many more documentaries like this in 2023, visiting companies working on radical new technologies and interviewing their engineers, and we simply would not have the budget to fund a production like this without Nebula. Our spin launch documentary, which occurred over multiple days and in 2 different states, requiring gear rental, hotels, camera operators, editors, animators, and more, ended up costing around $30,000 to make, a price we simply could not afford without your support on Nebula. So, as thanks, we will be uploading behind-the-scenes footage that did not make the cut to Nebula for any shoots like this going forward, along with our original series like the Logistics of D-Day and the Battle of Britain.